This is Saxon Advanced Math. This is Probability, Lesson 92A. And we're going to get into probability a little bit more in depth. A couple of terms that we've got to remember here, first of all. And the first thing is what the difference between mutually inclusive and mutually exclusive mean. And let's talk about like a coin, first of all. If I were to flip a coin, I have a 1 in 2 chance, or 1 in 2 probability of it being heads. And if it's heads, it can't be tails, right? If I flip it up there in the air and it lands and it's heads, it's not tails. Okay, so if I looked at the probability of it being tails, that's the other option, versus heads, which is the first option, I would say that it's 1/2 and 1/2. I add those together, I get 100% probability. So when I look at it that way, and the way the book reads it is the probability of either two mutually exclusive events occurring is the sum of the individual probabilities. Okay, now we also have to do some new terminology here. This little guy right here is union, and this is intersection. Okay, we often use union instead of or, right? And that's the union. This is the or. Okay, if we are using both, we're going to invert it, and we're going to call that the intersection. Now let's talk about our little example here we have with some marbles. And I don't have a white marker and a white board, so I outlined them here. But if I looked at it, I said there's 13 total marbles here on the board, right? There's 3 reds and 4 blues and 6 whites. And what's the probability of each one of them occurring? Well, the probability of pulling a red is 3 out of 13. The probability of pulling a blue is 4 out of 13. And then a white would be 6 out of 13. But if I take the time to add all those up, I end up with it being the addition of all these, which is 13 out of 13, right? That would be the favorable. What's the probability of pulling a colored marble? Well, or any marble is 100%, right? You pull a marble, it works out. So we're going to talk about some events here. Let's look at this, and we have 13 students. Okay, we have 6 girls and 7 boys. Of the 6 girls, we have 2 that have red hair and 4 that are not red-haired. We have 7 boys, 2 have red hair, and 5 are non-redheaded. And so I look at those and I say, you can be in both categories. The problem is that when we start to count these categories for probability, if I say, well, what's the probability of individually selecting at random a red-headed boy? Well, the Venn diagram here that looks really confusing to a lot of people. Let me explain what this is, because I didn't take the time to label each one of these dots. They said this is the group that are boys. This is the group that are girls. So outside of this circle are girls. Inside this circle are going to be red hair for this. And so when I look at it, I say there are 4 students that have, or 4 of these that have red hair, and I have 1, 2, 3, 4, 5, 6, 7 that are boys. Okay, so if I say boys with red hair, I would look at it and realize that I can't just take all of these and say, oh, there's going to be 2 that fall into both categories. It's still 2 out of the 13. Even though I have the probability of boys is 7 out of 13, and the probability of redheads are 4 out of 13. There's 4 out of 13 that have red hair. If I say the probability of boys that have red hair, I have to exclude the ones that are in both categories when I go to count that. So what I'm going to be looking at is the probability of R union B is the probability of R plus the probability of B minus the probability of R intersection of B. So I have to take these 2 out because they fall in both categories. All right? I can't count them twice. So in other words, it would be 4 out of 13 plus 7 out of 13 minus the 2 that have already been counted. And that's why I put here not counted twice. And that would give me my 9 out of 13. So when we're doing this, we have to take out the doubles. I'm not double counting those students. So I can't just come up with that probability. Now we can look at the Venn diagram and say, sure, there's 2 that match, right? And so that would work. But I have to be very careful with this because that 2 that match are in both categories. Okay? So, and this is the union. Now look at the example 92-1. A card is drawn from a full deck. What is the probability that the card is an ace or a black card? Now, when we're talking about this, we realize that how many aces are in the deck. Well, the first thing I'm going to do is say, well, there's 4 aces, 4 out of 52. Well, how many cards are black cards? 26 out of 52. But I've got 2 cards that are both black and aces. Okay, so I have to subtract out that doubled amount. Okay, and that's all we're doing is we're realizing that if I were to sit down and count every card or throw every card into a pile out of the 52 that met the category of or, I would have 2 cards that met the category of and so I'm getting rid of the and so that I'm not counting them twice. Okay, so, and if we had the deck of cards and we laid them all out and we circled them, we would realize 4 out of 52 would already have 2 of these cards of this, so there's really only 24 cards to be added. But how do I do that mathematically? I say, well, I take all 4 out of the 52 plus 26 out of 52, subtract the duplicate, and that gives me 7 out of 13 when it reduces.